When a single machine learning model isn't enough, we turn to ensembles. But the ensemble landscape is divided into two major philosophies: bagging and boosting. Bagging, which stands for bootstrap aggregating, builds models in parallel. It aims to reduce variance by averaging the predictions of many independent, deep trees. The most famous example is the random forest. Boosting, on the other hand, builds models sequentially. It aims to reduce bias. Each new tree in the sequence is built specifically to correct the mathematical errors made by the previous tree. It's a chain of continuous improvement. While bagging prevents overfitting, boosting turns weak learners into a single, highly accurate powerhouse. Before we can ensemble trees, we must understand how a single tree learns. A decision tree uses metrics like Gini impurity to find the perfect split. Imagine we have this 2D feature space with blue and red classes. The tree needs to find a threshold on the x-axis that best separates them. The Gini impurity measures how mixed a node is. If a node is perfectly pure, Gini is 0. We calculate the information gain for every possible split. The algorithm tests all thresholds and selects the one that maximizes information gain, giving us the purest possible child nodes. If all trees are identical, averaging them does nothing. Random forest introduces two sources of randomness: bootstrap sampling and feature subsampling, driving overall variance down. First is bootstrap sampling. We take our original dataset and create multiple subsets by randomly sampling rows with replacement. Second is feature randomness. At every split in a tree, the algorithm is only allowed to see a random subset of features, typically the square root of the total features. Mathematically, because the trees are decorrelated, the correlation coefficient rho drops. This means the variance of our ensemble drops rapidly as we add more trees, B. Within the boosting family, there has been a rapid mathematical evolution over the last 2 decades. Let's trace the lineage to understand when to use what. It started with AdaBoost, which simply reweighted misclassified data points. Then came gradient boosting machines, or GBM, which formulated boosting as gradient descent in functional space, fitting trees to pseudo-residuals. Next was XGBoost. By using a second-order Taylor expansion, computing both gradients and Hessians, and adding strong regularization, it dominated Kaggle competitions for years. Finally, LightGBM arrived, introducing histogram-based splitting and aggressive leafwise growth, becoming the undisputed king of speed and massive datasets. So, when should you use what? Here is the ultimate decision matrix. If you want a strong baseline out of the box with zero hyperparameter tuning, start with a random forest. If accuracy is paramount and your dataset fits in memory, use XGBoost. But if you have millions of rows and speed is critical, LightGBM is your best choice. AdaBoost, short for adaptive boosting, was the first major breakthrough. It literally tracks the errors of the previous tree, mathematically increasing the weight of misclassified samples. Imagine a 1D dataset. Our first weak learner, a decision stump, draws a threshold here. It calculates the error rate epsilon based on the weights of the points it got wrong. The blue point on the right is wrong. Using the exponential weight update formula, the weight of that misclassified point increases exponentially, making it visually and mathematically larger. When the next tree is built, it is forced to pay extreme attention to this massive, heavily weighted point, adjusting its boundary to correct the error. To truly master boosting, we must view it through the lens of calculus. Gradient boosting is simply gradient descent, but instead of updating weights, we update functions. Here is our data. We start with a simple model, just predicting the mean of the y values. The initial prediction f0 is the mean, but this has high error, How do we improve it? In standard gradient descent, we calculate the gradient of the loss function. For mean squared error, the negative gradient is simply the residual, the difference between the true value and our prediction. Now we train a weak decision tree to predict these red residual arrows. This becomes our first tree. We add this new tree to our ensemble, scaled by a learning rate. The model is now F1. Notice the residuals have shrunk. We repeat this process iteratively. Tree 2 fits the new, smaller residuals. Tree 3 fits the next batch, driving our loss towards zero step by mathematical step. XGBoost dominated by using second-order derivatives, gradients, and Hessians to find optimal splits. LightGBM took this further, using histogram binning and leafwise growth for unparalleled speed. XGBoost's objective function uses a second-order Taylor expansion. G is the gradient, H is the Hessian, and omega is a regularization penalty to prevent overfitting. XGBoost grows trees level-wise. It splits all nodes at the current depth before moving deeper, creating symmetric, balanced trees. LightGBM, however, grows leafwise. It scans all leaves and aggressively splits the one with the highest loss reduction, even if it makes the tree highly asymmetric and deep. Let's look at a hands-on code simulation to see how these models differ in practice. Here is the standard implementation for a random forest in scikit-learn. We instantiate the classifier with 100 estimators. Because it relies on bagging, the decision boundaries it generates are an average of many deep trees. If we plot the decision boundary, we see it is highly smoothed. The voting mechanism smooths out the rough edges, preventing the model from overfitting to noisy data points. Now let's switch to LightGBM. Here we specify a learning rate, which controls the contribution of each sequential tree, and num leaves to control the aggressive leafwise growth. Notice the difference in the decision boundary. Because boosting aggressively targets the residual errors, the boundary tightly wraps around the complex regions of the data. It is highly accurate, but without proper tuning, it can easily overfit. Understanding these trade-offs, parallel versus sequential, variance versus bias, is the key to mastering tree-based ensembles.